and thanks to the organizers for the opportunity to present this work. I'm a bit sick. I hope it's going to be okay. But if you don't understand me because my accent is even worse than ever, please tell me. It's fine. Thank you. So I'm going to take it from where the previous speaker stopped. So maybe we are going to be out of work in a month. So I'm going to motivate new things to do. One of them are using binary pulsars to probe the dark sector. In this talk, I will talk only about dark matter, but maybe things that we are doing may also be relevant to detect dark energy, well, so in some scenarios at least. The talk I'm presenting here is based on two papers, one done with Sergey and Diana Lopez-Nasir, and the other one with Andrea Caputo and Jesus Zavala, which is quite recent. Though, as you will see in this first slide, there are many things that seems to be possible and that have not totally been explored. So let me set the stage, since I am switching, I think, the observables from the previous talks. My observable is going to be the signal coming from a binary pulsar. So binary pulsar, a system where there is a pulsar and another object, and they are orbiting each other. Okay, so this signal is emitted, it propagates through a medium, and then we eventually are able to detect it. And you know, this is such a precise measurement. The time of arrival. The main observation here is the time of arrival of the pulses. The pulses are you know, this is a kind of lighthouse, and it's rotating, and it's very precisely stable. The time of arrival of the different pulses are telling us many things. In particular, they are telling us how this orbit looks like, right? Because of the, you know, if this guy is here or here or here, the pulse comes before or later. And it's also telling us, well, this I'm not going to touch, but these pulses have some structure, and they can be used to understand properties of neutron stars. I'm not going to touch this. What I'm first going to emphasize is that anything that happens at the level of the binary, either extra radiation or extra interactions, we may be able to constrain it through the study of the time of arrival. And also, if there is a medium in which this binary lives, also we may see that the medium, and that's, by the way, that's the main message. The medium in which this binary pulsar lives is going to modify the orbits if there is some interaction, and then this you may be able to detect. There's more than that. Also, the radio wave is propagating in the galaxy. Well, before it propagates in the magnetosphere, this also can be interesting. I'm not touching it. But maybe easier to describe is the propagation in the galactic medium. The galactic medium, I mean interstellar medium. Also, there is a gravitational wave. If there is a gravitational wave background, you may affect the time of arrival, and this is used in what is called PTAs to detect stochastic backgrounds. Also, there is a dark matter medium, and this has been also explored in some regimes. And whatever happens in between that modifies the radio wave may also be at least studied, and you may constrain what happens in between. And finally, detection. And detection, by this I mean things like, for instance, that this is such a precise signal that if there is something changes the fundamental constants at different places in the universe, you may look at different pulsars, and you know, if this is time dependent, you may also constrain it. As I say in this talk, I'm only going to talk about dark matter, but well, all of us working on this, we have different ideas of how to extend to other things. And in particular, I'm only going to discuss what is already published, and this is the way in which the dynamics of the binary system is modified by the fact that the binary is not alone in the universe, but living in a medium. Okay, so that's what I'm going to do. Dark matter evidence is quite solid, right? And I think it's important to emphasize that it's coming from different scales. well, that we all are aware of. You can try to modify gravity or do whatever with the equations, but you have to explain all this phenomenology. This is a very solid picture, but precisely the dream in this field would be to directly detect it. And by directly detect it, I mean not only in labs, but to look for phenomena in the universe that are local, like are really some dynamics going on, and there, the fact that there is dark matter modifies the dynamics. Well, of course, those are these kind of probes, but I mean something that which has time scales that you dominate better. Well, yeah, local searches. Well, the standard way to look for dark matter in local searches, there are two main ways, direct or indirect. Direct is by basically seeing the recoil of something in a big tank, okay? And this assumes that dark matter interacts with the standard model particles through some kind of effective vertex. Or, well, indirect, which basically you assume that the dark matter in the universe is also interacting or decaying into standard model particles, and you detect the final outcome. And those are very active fields of research, and I don't want to say more about that. Because these fields of research, most of the scenarios that they are testing are WIMP scenarios, okay? But if you come to this field with a fresh mind, the first thing that is quite shocking is that the landscape of dark matter is huge. Okay, so it's not at all restricted to a WIMP, and in particular, if you even the simple, well, the only thing that you require is that this candidate is something that clusters, and as I said before, it's very important. It clusters at all scales. I mean, it's not, you cannot just focus on a particular observable. You have to try to explain everything. But even with this trying to explain everything in mind, the simplest thing you can ask for is which is the mass of this candidate if it is a particle, and well, any mass between 10 to the minus 24 and whatever, okay, is allowed. And this whatever can even be compact objects. So dark matter can be compact objects. There is, however, different thresholds that if you pass them, you have to change your description of how dark matter, well, what is the best way to describe dark matter, even if it is a collection of particles. For instance, if the mass is below the electron volt, as Sergei said, below 0.1 or something electron volts, then in dark matter you know more or less the density that you have in our halo, and that means that the number density, if the mass goes down, gets very high, and so high that at this point the best way to describe this medium is as a classical field. And also if you go to the other limit, at some point this is not it's a distribution of particles, it's a distribution of compact objects. Very important, I think, but I'm not going to touch it, is that for dark matter it's better if you have a way to generate it. And well, as you see, all this, what I'm going to the different points of this slide make WIMP candidates desirable, but they are not the only possibilities. For instance, for generating mechanisms, the constraint that one can put is at kilo electron volts. This is somehow the minimum mass that you can have if this was produced thermally. But if the production mechanism is non-thermal, and there are some mechanisms for that called freeze-in of phase transitions, then this bound disappears. Okay, so you can really populate the universe with dark matter up to any mass you want, in a sense. For compact objects, I'm not at all an expert on this, but I think there are different proposals on how to generate it. In the case of WIMP, this is the standard. And with the standard cross sections, weak scale cross sections, that this is well understood. And finally, and this is also a very active field of research nowadays, the detection strategy of the different candidates change a lot depending on the mass. And by detection, I mean direct. Something that is important to keep in mind also is that the typical momentum of these particles, if they are particles, is getting very, very low as the mass goes down. And what does it mean? It means that if I want to have a recoil anywhere, even if I build the most precise tank of xenon or whatever, at some point this momentum is so low that nothing's going to happen ever. So I can wait for the edge of the universe, and I will never get a detection. Okay, and this puts about, it's not GeV, it's around some EV, but there is no way to, there is a threshold there. That's why people nowadays are looking for other ways to detect dark matter in this very interesting region. And they are based more than in building a huge detector on precision tests that don't require, that's important, they don't require momentum transfer. There are things that are quite different. Oops, sorry. Well, for compact objects also, I mean, luckily for us, we are not being crossed by these guys. So it's not that they are going to be detected by recoil. Okay, so that's kind of the landscape. And in this talk, I'm going to describe ultralight, but also particle-like dark matter candidates. So that's the question that I want to answer. Does dark matter change the motion of a binary? And the first thing I'm going to do is to describe dark matter as a collection of particles. Okay, there's a medium. Here is represented by this grid. And the binary system is moving with a certain velocity with respect to the medium, okay, and otherwise is just orbiting. Now, each of these members of the binary is interacting with the medium, at least gravitationally, right? So that's the less we have to ask to dark matter is that they interact gravitationally with it. That means that as they move through the medium, they interact with the medium, which generates a force. I'm going to be more explicit there. This force is well understood. It's called dynamical friction. And it's going to basically, if they move with a relative velocity with respect to the medium, it's going to try to pull down from these guys. Eventually, that means that the orbit is going to become less and less relativistic. So you are losing velocity of the guy. But there is also a different effect because the center of mass is moving. So also there will be a center of mass deceleration. Well, this should be deceleration with respect to the medium. Okay, in this case, it's the dark matter. The dark matter in the halo is at rest, in principle, and the disk is rotating, and this is basically the wind velocity coming from the disk, rotated with respect to the mean velocity of the halo. Here they should be equal. Okay. The center of mass acceleration is not very important in my talk because you can determine it, but it's full of systematics. Basically, where you are in the galaxy is going to change this a lot. The main observable for binary pulsars is the relative acceleration, so how the orbital parameters are changed as the system evolves. Okay, and this force can be decomposed in different components, and one of them, well, I'm going to be more explicit here. Okay, so the force is described here. So as I said, the force that these guys experience, I here represent each of the members of the binary. It's there because you are moving with respect to the medium, and then that means that while you are moving, you are attracting the particles towards you. But since you move, what you generate after you is a wake, and then this wake, this overdensity, is back reacting over you, right? This is the effect. This is why this effect is a G squared. So you first need to accumulate the dark matter, and then dark matter pulls from you. Okay. This is why this force is also proportional to the relative velocity. If you don't move, this is not there. This force. And basically, it's also, well, this, by the way, this you cannot see from here because there is, there's some cancellation. So this goes to 0 if the relative velocity goes to 0. It also depends on the dispersion of the medium. So how if the medium is very dispersed, this wake is not going to be very coherent. So it's not going to really generate an overdensity that pulls from you in a precise direction. And that's why it's important, the dispersion of the medium. And finally, it depends on the density of the medium. So this is by the way, this is what Chandrasekhar derived long ago, and this is present in books in cosmology, in galactic dynamics. This formula is okay if the velocity of the orbital members is slow with respect to the dispersion. Otherwise, you have to be a bit more careful, in particular if you are talking about binaries. And the reason for that is that if the velocity starts to be faster than the dispersion, it may happen that this is the force of one wake over you, but if you are fast enough, you may encounter the other wake before it dissolves. So you can understand that once you are not in this regime, things are different. But anyway, you can then go and study slow binary pulsars. And here is the order of magnitude of the effect. So the PV dot is the time derivative of the binary period. I took this formula directly from Pani, who is the first person who derived it for the binary pulsars, where he did a trick. And the trick is that, by the way, this lambda is it's a parameter of order 20. This is this ratio is order 1. This can be order 1. This can be order 1. But here he put something which is not order 1. In principle, the density in our, most of the pulsars that we detect are in our environment because of selection, because radio waves are not very strong. And in our solar system environment, the density of dark matter is this one. And you see that this already tells you that the deceleration that you expect from dynamical friction is at least 2 orders of magnitude smaller than what you have ever detected. This detection is with the best possible system. That is not what you are going to have for slow pulsars. Well, the way to recycle it is to say, well, let's try to look for pulsars in the galactic center, and maybe there the different halos will produce a bigger effect because you are proportional to the density, but this is not guaranteed. Also, timing close to the galactic center is very difficult. What we did was to recycle it in a different model of dark matter, which is a model a bit more, with more structure. It's a model in which the dark matter also generates a disk, okay? And this disk of dark matter is first more dense and also has a smaller dispersion. So these two things, these two numbers are now boosted, and they are boosted to the level that you may be able to probe this dark matter candidate with the current and near future observations. And it's a bit more complicated than that. The analysis requires revisiting everything in this paper, but the final bound on what is the final effect on this PV dot for a particular system here. It is something that I have to be a bit fast, sorry now, but we can discuss later. The important thing is that the ratio between theoretical number in this scenario and the detection is order 100. That means that this may be better constrained in the future, in particular because slow pulsars, slow binaries are not very well timed, also because of lack of time. So people in the pulsar timing community prefer relativistic pulsars, and those are timed only from time to time. So if they start looking at these guys and do a better data analysis, this number is going to be better. So the point is that we are close to really see this medium. Now, the second part of my talk, which I tried to finish in less than 5 minutes, is this was for the particle description. You can also do something for the ultralight description. Remember that there was a talk about this yesterday. The idea is that if the mass is smaller than this number, the occupation numbers are very high, and it's better. You can do whatever you want, but it's more convenient to describe this as a field. And this field has a field equation that, in particular, for the massive scalar case is very simple, and that's very important. This guy is created very coherently in the early universe. I'm not going to touch how this happens, but this is a natural scenario. And if this happens, then you generate you generated in a displaced field in the potential, and at some point when the Hubble when the Hubble is smaller than the mass, then you start oscillating here. This behaves as a cold dark matter if the mass is large enough, because of the it's going to oscillate, but the pressure averages to 0. And the important thing is that eventually these oscillations, they are there. So they are there means that if you compute the gravitational fields in the presence of this scalar field, which is oscillating, they will average, the part which is not pure cold dark matter averages to 0, but the time scales at which they don't average can be of order years. So in principle, if you look at observables which are order years, they are there. Now, for the binary pulsars, this is okay. I mean, the typical binaries are days. So the idea is that in this case, there is also there's a key difference is that you are not now creating the wake and then the wake interact with you. There is a medium already. There is the Newtonian potential from the galaxy that is oscillating and is modifying your orbits, or even more, it can be even stronger, the fact that this new scalar field, you can directly be coupled to it. So you don't need to rely on the gravitational field generated by the galaxy. You can also try to precisely constrain how strongly you can be coupled to dark matter, okay? Because the dark matter field is also oscillating, so each of these bodies is gonna be pushed back and forward. Well, once you go solve the equations, you realize that for the pure gravity case, sorry, I'm being a bit fast. I was optimistic with my time. For the pure gravity case, the typical effects that we get, this is the mass of the candidate, okay? These are the places where you find a binary pulsar with this timing, you could be able to say something about them. And normally they are always, far away from being, this is the best you can detect. But as I said, the best you can detect is for binary pulsars which have periods. Here is the period of this form. So in principle, for this case, we need either to go to, you cannot really say much with binary pulsars. But for the direct coupling, yes. So the direct coupling, let's say that my massive particles interact with the scalar field through a linear or quadratic interaction suppressed by a scale, and then I can try to put bounds on this scale. Okay, because as I said, eventually what is going on is that my orbits are happening, and there is something pulling back and forward. You can resonate. Well, physically, what can happen is that you can resonate with it, and whenever you resonate with it, this can accumulate. And in this particular case, is where you get very, very strong constraints. And these constraints, we put them in this plot. Let's look at this one, for instance. And they are represented by small dots, or for different pulsars. And the reason why they are dots and there's not a line is that, as I said, the strong constraints happen at the masses that resonate with the frequencies of the binaries. Those are different harmonics of the resonance, and we don't really know what happens in between. So this resonance is not exact, so you can deviate a bit from it, but in the middle there should be something that we don't know yet how it looks like. Okay, so let me conclude. The main message, independently of these particular two papers, is that the signals from the pulsars test the motion of the pulsars in the medium of dark matter, in principle also of any medium with which you interact. There are two different casuistics. Oh, do you say that? First, if you can accumulate a wake behind you, there is this dynamical friction effect, okay, that is gonna slow down your orbits. But in principle, for the standard cold dark matter paradigm, it doesn't work unless you go to the galactic center or you start exploring more complex dark matter candidates. There is also the other possibility that the medium is already generating an effect. And in particular, this happens if you have these very low masses for dark matter, where there are coherent effects in the background. And this is efficient, in particular for the case of direct couplings. I didn't say this, but also because in these scenarios of ultralight dark matter, you may have regions in the galactic halo where there are huge overdensities. Okay, and there are more things to do. And I thank you for your attention. Thank you.
In the model with the dark disk, can you comment what's the reason for the suppression of velocity dispersion? It's a pretty significant suppression. Yeah, and also related question is that in this case the velocity of pulsars, orbital velocity is larger than the dispersion.
Yeah, yeah.
So to what extent the calculation is applicable in that case?
For the first thing, well, the way the dispersion is this one because the way you generate it is as happens in our disk, is because of in these models there is dissipation. You start with a halo, and then the different particles get ionized, and they start. You need to have a dark photon that basically takes away all the the energy, but keep the angular momentum. And eventually, you generate a system which is, which is more co-moving, and that's why the dispersion goes down.
So, how does it compare with the dispersion in the normal baryonic disk?
Yeah, I think is
lower. It seems to be, or is it the same?
I think it's the same. We can look at this. Yeah. And for the second one, yes, as I said, that's why I said that it's not just that you take this formula and substitute these numbers and you get the result. Mm-hmm. The problem with what we did is there is no, and that's maybe there is no the numerical study. This at some point it has to be studied numerically, because you cannot apply a good. There is no approximation that applies in this case where the velocity is of the order of sigma, and there are no numerical studies of a binary in a collisionless gas in this regime. What there are studies of a binary in a gaseous medium, and what we have done is take these numbers, see if they reproduce what we know about this case in the collisionless case, see that what we do seems to be correct. But these numbers is not the final answer for sure.
It seems to me that for almost all, let's see, what is the velocities of these guys? It seems to me they should all be much larger than even the virial dispersion of halos for the observable.
Because of the supernova kick? Or which velocity, sorry?
The orbital velocity.
No, the orbital velocity, we are talking about very non-relativistic guys, so 10 to the minus 5 C. Yeah.
So what's their orbital period then?
Days, 10 days. Yeah. 10 to the minus 5, 10 to the minus 4, yeah.
You're saying two solar mass objects with a period of a few days has a speed of light.
Maybe I'm wrong, but
that low, really?
I think so, yeah.
I did the Earth speed is already 30 kilometers a second, right?
Well, maybe they are more far away. I don't know.
This is just Kepler, right?
Yeah, it's Kepler. That's true.
Anyway.
Well, I did the. Yeah, I cannot compare with the Earth. They are separated by one. Yeah, they are separated by one light. Let me see. I checked it before. Well, I can tell you later, but we can check.
I think they will be comparable actually.
I checked it before, and this is 10 to the minus 4, 10 to the minus 5. If you are really going to the very, very 100 days.
I think it should be 10 to the minus 4, 10 to the minus 3.
For those of some days, yes, I think so.
For those of 10 days.
Yeah. That's why you are talking about the, even talking about the standard case of PANI is not your borderline. So this is a, as I said, here we need someone who does a simulation with the embody and tracking very precisely a binary. I don't know, I cannot do it.
Okay, so then
Yeah,
thanks again.
thank you.